So we will now prove that the mean minimizes the mean squared error for the constant model using a different algebraic trick. So we're going to do this by hand, but not via calculus. An intermediate fact that we will need in this proof is that the sum of deviations from the mean is equal to 0. Now the sum of deviations is the sum of values, so yi, minus their mean, y bar. And so y bar is just the mean of y. Okay, and we want to prove that this quantity is equal to 0. Now it's not immediately clear why this will be useful, but trust me on this, we are going to need it momentarily. So we can progress with the properties of sums. So we know that we can write this as two separate sums, the sum of our yi's minus the sum of y bar. Now the sum of our yi's, we can't really simplify that further, but y bar is a constant, right? It is not impacted by the index of summation I, and so this is really just y bar plus so on and so forth plus y bar. So I can write this as n times y bar. But the definition of y bar is 1 over n times the sum of all of my y's, right? Because that's the definition of the mean. Make some space here. And so the n and 1 over n cancel, and I'm left with the sum of y's minus the sum of y's, which is 0. What this is saying, like an example of what this is saying, is if you take a bunch of values and sum them together, it's the same as if you sum the average of all those values that many times. So like 1 plus 2 plus 3 plus 4 plus 5 is the same as 3 plus 3 plus 3 plus 3 plus 3, for instance. And so this quantity is equal to 0, and we will need that fact. Another definition that we will need is that the sample variance, or the variance of a sample, is 1 over n times the sum of yi minus y bar squared. And now, this looks very similar to the mean squared error for the constant model. And indeed, it is the mean squared error if we choose y bar to be our model. And you know from the last video that y bar is the value of theta that minimizes average loss, but we will take a look at this in more detail momentarily. But for now, let's, go back to the task of actually determining how and why the mean minimizes average loss. So how this proof will progress is that we will rewrite yi minus theta cleverly as yi minus y bar plus y bar minus theta. Now, again, this might be one of those things that's kind of coming out of nowhere, but this is the kind of algebraic manipulation that you become familiar with more and more practice. And why is this valid? Well, it's because the minus y bar and positive y bar cancel out and give you 0. And so I can write this as yi minus y bar in brackets plus y bar minus theta, also in brackets. And so what we can do is substitute in this relationship into my formula or expression for average loss. And so I get 1 over n times the sum of yi minus y bar plus y bar minus theta. Now this is all squared. Now what I can do is expand the square using the properties of the multiplication of binomials. And so with that, I get yi minus y bar squared plus 2 times yi minus y bar times y bar minus theta. Let's get a little more space here. There we go. Plus y bar minus theta squared. And so we've just expanded the square from the second line. Now what I will do is distribute my sum into each of these individual terms. What's important to note is that with respect to the sum over I, y bar minus theta is a constant. So these are not part of our summation, and we can sort of pull them out, and you will see that we were about to do that. So what I can do is rewrite this as 1 over n times the sum of yi minus y bar squared. You can see that this looks a lot like the variance, plus 2 times y bar minus theta times this sum of yi minus y bar. And you can see that this is the quantity that we just established to be 0 at the start of this video, plus n times y bar minus theta squared. The reason this is n is because, again, this is a constant with respect to I, and so we're just adding it to itself n times. And so if I distribute the 1 over n, I get 1 over n times the sum of yi minus y bar squared, which is just the variance of y, as we just established, plus 2 over n times y bar minus theta times the sum of deviations from the mean. Now, a couple moments ago, we just established that this quantity was 0, so I will write times 0, and so this middle term actually vanishes. It's equal to 0. Now, plus y bar minus theta squared, because the 1 over n and the n sort of cancel out. And so I'm left with the variance of y, sigma y squared, plus y bar minus theta squared. And again, this is equal to my average loss for the given choice of theta. And what I want to do is minimize average loss, right? And so the variance of y's is fixed. We can't really change that no matter what our value of theta is. So we can sort of ignore it for the purposes of minimizing average loss. And so now our job is to figure out the value of theta that minimizes this second term. We know that this is something squared. Something squared is always greater than or equal to 0. In order to minimize it, we need to set it equal to 0. And that happens when that happens when theta is equal to y bar. And so when theta is equal to y bar, that minimizes our average loss. And so this is, once again, a proof that theta hat, in the very specific case of the constant model, when we are using squared loss, is the mean of our y's. Because setting theta equal to y bar makes this quantity as small as possible. And so this property that we've determined in a variety of ways holds true for any data set, but is only true for this specific combination of model and loss function. If we choose any other constant than the mean, the empirical risk or average loss will not be as small as possible, and so our model won't be the best in some sense, and so it'll be worse. And so this shouldn't be that surprising. This explains why we so often use the mean of a set of values to describe it. It's not only convenient to calculate, but it's also the best in some sense. And so here we write theta hat because it is the optimal value of the model parameter theta for our given choice of model and loss function. One thing you might note is if we substitute in y bar, or the mean of y's, back into our average loss function or our empirical risk, the result we get is the variance of our y's. That means the smallest possible value that the mean squared error can take on for the constant model is the sample variance. And that's an interesting result that you should keep in mind as we move on to looking at more complicated models.